This is going to be part 2 of our Unit 4 Chemical Interactions review. So this is going to be 15 through 36. So the first one, it asks you to balance and identify the type of reaction. And so first off, since we got aluminum and calcium all by itself, do those last. And looking at this, looks like we got to find the lowest common multiplier for the 3 chlorines and the 2 over here. You zoom in a little more. And the lowest common multiplier is 6. So we're going to put the coefficient 2 in front of this one, because 2 times 3 is 6 chlorines. And now we need a total of 6 chlorines here. We'll put the coefficient 3 in front. Now at this point, now it's real easy to finish balancing this. We've got, let's see, well, there's that invisible subscript 1 times 3 is 3 calciums. So we'll just put a coefficient 3 right there. Over here, let's see, in the reactants, now these are known as the reactants. In the reactants, we have 2 aluminums, because we've got 1 aluminum in each one of the aluminum chlorides, but we have 2 of those. So we need a coefficient 2 there. That's balanced. Now what's happening is calcium is coming into this reaction, and it's going to kick off aluminum, leaving aluminum by itself. So it's a replacement. You can probably figure it out from there. Oops. Let's see, number 16. Explain how many atoms and elements are in this. So first off, let's do atoms and elements. Okay. Well, first off, elements. We've got oxygen, iron. 2 elements. Oxygen and iron. That's it. Now, the number of atoms is going to be different, because part of the law of conservation of matter is you cannot create or destroy these. So now when we take a look, we've got 3 times 2, 6 oxygens right there. Here we've got 4 irons. So over here in the reactants, altogether we have 10 atoms. And then over here, we should end up with 10 atoms over there. Let's see, 2 times 2 is going to be 4 irons. 2 times 3 is going to be 6 oxygens. That adds up to 10 atoms. So we haven't created or destroyed any atoms. We've just rearranged them. And it looks like here we've got 2 different chemicals joining together to make one. So you can look on your list. That should be pretty straightforward what type that is. Number 17 asks, what's the charge on an aluminum ion? And let's see, and then it asks, is this a cation or an anion? Well, way to figure these out, aluminum, you look on your periodic table, it's over here in group 13, which means if you did the Lewis structure, it would have 3 valence electrons. And aluminum, being a metal, it's going to lose those electrons and become stable. It's going to throw them away, causing it, when it throws those away, you're going to end up with aluminum with a +3 charge, because it's lost, each of those electrons there were a negative charge. So now it's going to be +3. And my memory clue is cation. That T, turn that T into a big plus sign, and that'll let you know whether you got an anion or a cation. The octet rule. Octet means 8. Wanting to be so elements, there's only a few elements that are noble gases on the periodic table. They all have 8 electrons around them, except for helium. It only has 2. Let's see. So it says the octet rule states that in compounds, atoms tend to have their orbitals full of 8 electrons. So there's that one. And the next one, how many electrons does barium have to give up, to achieve noble gas configuration? So, hold on a second, got to grab a chart here. So, the element barium, so right over here, now you might need to take time to find it in the periodic table, but whoops, there we go. It's right there. It's in the alkali earth metals. It's in group 2. So let's see, barium, if we were to draw its Lewis structure, make sure I keep this centered here. Barium would have 1, 2 valence electrons around it. And how many electrons does it have to give up? Well, it has to lose those 2, because when it loses those 2, barium sitting way down here, whoops, let me zoom out here a little bit, sitting way down here on the periodic table, it now, when it loses its 2 electrons, it now thinks it's xenon, but it does have a plus charge, because all metals always have a plus charge. Let's see, what's the formula for the ion formed when potassium, now it's not P, it's K, it's potassium, achieves noble gas configuration? Well, potassium, so let's take a look. Come over here, it's in group 1, which means it has 1 valence electron. I'll just put that over here on the side, and let's see, well, potassium's a metal, it wants to lose that electron, so when it loses its electron, that's a negative charge there. When it loses that electron, when it throws it away, it'll have a +1 charge. So looking at the big picture, potassium sitting right over here, when it loses that 1 electron, it now believes it is the element argon. So what's the formula for the ion when it achieves noble gas electron configuration? Well, and we tend to write this like this. We'd say potassium, and we'll put a plus sign like that to show that it's lost it. How does an ionic bond occur? Well, that's when you have a metal, like the most common one we got, sodium, with 1 valence electron, bonds to, let's use our good friend salt, which is partially made up of chlorine. Chlorine is in group 17, so it's going to have 7 valence electrons around it. And an ionic bond happens when a metal gives an electron to a nonmetal. The nonmetal becomes a plus ion, or a cation. The chlorine over here, when it gains that negative charge, it becomes a negative or an anion. My memory clue was that negative sign always reminds me kind of the cross in the A in the word anion. Number 22. How many valence electrons are transferred from the potassium atom to nitrogen in the formation of the compound K3N? And what type of bond is this? Well, first off, that's probably the easiest one. Potassium is a metal. You might have to take a little bit of time, but if it is on the left side of this zigzag chart, which it is, it's a metal, and then nitrogen's a nonmetal. So how many valence electrons are transferred from the potassium atom to the nitrogen? Well, what happens is, let's get this drawn here. Nitrogen is in group 15, so it's got 5 valence electrons. And so every potassium, like we talked about before, has only 1 valence electron. So each potassium is going to give 1 valence electron, but you're going to need 3 of the potassiums altogether. So there's going to end up being 3 valence electrons moved around in there. Hello, Mr. Lake. Mr. Lake is visiting us. Let's see. Number 23. What's the formula when a sodium cation and a nitrogen -3 create a compound? Well, that's where we use the crisscross method. So you come over here. I'm going to have to scoot off to the side here. So sodium with a +1, nitrogen with a -3. You do the crisscross, NaN. Now see, that 3 becomes Na3. Since that's a 1, it just becomes that. So actually a chemist would just write it trisodium nitride, like that. That's what it would be. So I'd use crisscross on those. Same thing over here for number 24. We've got aluminum and O2, so we know we're going to get aluminum oxide. You always put the metal first. Now do crisscross, the -2 just becomes a plain old subscript 2 for the aluminum, and over here that becomes a 3. And now we got Al2O3, so that's going to be the formula for, and that would be called dialuminum trioxide. Okay, so we've got another formula problem here. So we're going to end up with sodium sulfate, SO4. Now I'm going to put parentheses around that one, and we're going to call that a -3 on there. So now, oh, that's a +1 to start with. So when we do the crisscross, we've got to put that 3 over here, and that 1 right there. So it becomes, when we clean it up, sodium 3, or trisodium sulfate, or you can even say sulfate, excuse me, if you wanted to. I think I got a cold coming down here. 26. Which type of elements form ionic compounds? Let's see, you get metals bonding to a nonmetal. Or you could even say positive ions, called the cations, bonding to negative ions, or anions. What force holds the ionic bonds together? Well, that was the first things we worked about. It was in our packet. You can look that up in your packet on the very first assignment we did. Let's see. I'm going to make you have to do a little bit of work here. So in our packet that we first started with on here, we've got some good information on here that can actually, this is a really good study aid for you as well. But our very first assignment, you read up here, it'll tell you right up here what type of bonds they are. So that's where you'll find that answer in your first packet on the very first assignment we did in that. Number 28. Oh, better zoom in now. Why do atoms share electrons in pairs in covalent compounds? Well, that's just the way the universe works it out. So we'll see that here in a moment when we take a look here. What are they trying to become? So when they share electrons, they're going to become stable, which means they kind of find a way to satisfy the octet rule without having to give or take electrons. So for example, for nitrogen here, I'm going to do 2 of those. Nitrogen is in group 15, so you take a look on the periodic table, 15, which means it has 5 valence electrons. 1, 2, 3, 4, and I'm just going to put the other one there. 1, 2, 3, 4, 5. So it's pretty obvious those two are going to team up and share. Those two will team up and share, and those two will. Sometimes this might be redrawn like this. They might redraw it to show that one right there has 2 dots, that one has another 2 dots, this one has another 2 dots, and then a nitrogen like this. So you may see it set up like that. Chemists tend to get lazy. They'll just tend to do this. They'll just show it like that because they know that there's going to be some unbound electrons. But that's the proper way. O2, now this is what we call this is a triple bond. There's 3 pairs of electrons being shared there. So now we've got oxygen over here, 1, 2, 3, 4. I think it's in group 16. It is. Now I'm just going to go ahead and put the paired electrons like this. I'm just going to keep them away from the other oxygen. 1, 2, 3, 4, 5, 6. And those two will team up, and those two will team up. So you get a pair of electrons. So when they share their electrons, they're going to be sharing in pairs. Here's 3 pairs shared. If we clean up this diagram, a chemist might draw it like this, showing a couple of lines, and then they can put a couple of dots over here, and we got to get those dots there. And we look at that, 1, 2, 3, 4, 5, 6, 7, 8. Every one of these has 8 electrons around it. And calcium, how would you, the Lewis structure? Well, the Lewis structure for calcium ion, +2. When you start with, I'm going to draw this lightly, calcium is in group 2 of the periodic table, it has 2 electrons, but since it's an ion, it's going to throw those away. So when it throws those electrons away, it now thinks it's going to be the element argon, so it's nice and stable and happy, but it does have a plus charge with it. And CO2 over here, well, carbon's going to be in the middle, 1, 2, 3, 4. Carbon is in group 14, right in the middle of the valence number of electrons, and it's going to have an oxygen on each side. We know from a previous one that oxygen looks something like this. I'm going to, let's see, what shall I do? I'll just make these 2 over here. So 1, 2, 3, 4, 5, 6. Make another oxygen over here. 1, 2, 3, 4, 5, 6. So what happens now, let's see, those 2 electrons are going to team up, and those 2 will. Those 2 electrons will team up. Oh wait, let me fix that, sorry. Let's make this unpaired here. That'll team up there, and this one will team up with that one. So I'm just going to kind of clean this up now. It's kind of messy. Let's redraw the carbon. It's got these 2 lines coming to an oxygen, with the oxygen having its 2 unshared pairs of electrons over here. This one would look like that. And there you go. We got that. What's the Lewis structure for the following compounds? So we're going to do C2. So we know when we do C2H6, we're just going to put 2 carbons, because carbon's going to be in the middle. Every carbon is going to have 4 valence electrons around it. Let me zoom in here a little bit. Okay, and so what's going to happen is these two are going to team up, but now they need to team up with a hydrogen. Now hydrogen is in group 1 of the periodic table, so this hydrogen will share its one electron there, and another hydrogen right there, share that one, another one here, they share. Oops, squeezing this in an awful lot, right there, and another one there, hydrogen. So if I clean this one up, let's see, I'm just going to come up here to the top. When we clean this up, all of those little dots together, we end up getting a pair of electrons shared there, and then you get hydrogens like this. This is called a structural formula, but the structural structural formula is based upon a Lewis structure where you could just put little dots around and it shows the pairs of electrons that are being shared there. Now with this one over here, C2H4, so we got the same thing as before, 1, 2, 3, 4, 1, 2, 3, 4, but now we've only got 4 hydrogens to team up with. So I'll put that, 2 of them there, we'll put 2 over here. I'll put a hydrogen there, it's taking that one, I'll just do this one here. So what happens is now, with this carbon, this electron here needs to share with that one, this one here needs to share with that, and to clean this one up now, this is a double bond in between those. So now we're going to have 2 carbons, 2 double bonds there, and then we have the 2 hydrogens coming off. And so that was just cleaning up this one. Okay, each of these lines I drew connecting just represents electrons. And now the octet rule is satisfied. Every carbon is surrounded by 8 electrons. Every hydrogen has 2. And then what works out for this one here, same kind of idea. You're going to have your 2 carbons over here. But now each one only gets 1 hydrogen to share its electron with. And now those 2 are going to share, those 2 will share, and those 2 will, and you end up with something that's called acetylene, very high energy, like that. So that's what that is. Okay, with that right there, I'm going to stop. Almost done, but I need to take a break.